Hi, welcome to my presentation. My name is MD Yusuf Harun. I am a PhD student at Rochester Institute of Technology, Rochester, New York. Today I will present our paper GRASP, a rehearsal policy for efficient online continual learning. This paper has been accepted at CoLLAs 2024. Code to implement GRASP can be found on our project website. A link to the website is given in this slide. Continual learning in deep neural networks involves incrementally accumulating knowledge in a deep neural network from a growing data stream. A major challenge in continual learning is that non-stationary data streams cause catastrophic forgetting of previously learned abilities. A popular solution is rehearsal or experience replay. Rehearsal-based methods store observed data in a replay buffer and then iteratively retrieve a subset of data from the replay buffer to update the deep neural network. It has been a common practice in continual learning to constrain the replay buffer where a certain number of examples can be stored. Rehearsal is inspired by neuroscience where recent memories are stored in the hippocampus and then reactivated for long-term consolidation. Rehearsal methods fall into three categories: veridical, latent, and generative. In veridical rehearsal, raw input data is stored in a replay buffer for later rehearsal. Instead of storing raw data, latent rehearsal methods store features from hidden layers, allowing them to store far more samples than veridical under the same memory budget. If storing data is prohibited, generative rehearsal methods produce synthetic images or features to retrieve old knowledge. However, generative rehearsal struggles with feature drift issue. In our work, we conducted experiments in both the veridical and latent rehearsal settings. Rehearsal algorithms alternate between a sample acquisition phase where samples are added to a replay buffer and a rehearsal phase where the deep neural network is updated using the replay buffer and newly acquired samples. This prompts two questions. First, what do we store or remove to maintain a constrained replay buffer? Buffer maintenance policy deals with this question. And second, what do we retrieve from the replay buffer to update the deep neural network? Rehearsal policy deals with this question. A rehearsal policy governs which samples are selected to update the continual model. The most common approach is uniform sampling, but better policies can potentially reduce the time required for rehearsal. Therefore, the goal of our work is to create a rehearsal policy that can efficiently update the continual model so that it achieves maximum accuracy while using fewer network updates. While buffer maintenance policies have been heavily explored in continual learning, much less work has been done to identify which stored samples should be selected for rehearsal. Current state-of-the-art methods except MIR and SR mainly proposed buffer maintenance policy and used uniform random as a rehearsal policy. Most of the current methods are computationally expensive and difficult to scale. In contrast, our method GRASP is efficient and scalable. We compare GRASP with 17 other rehearsal policies, including the state-of-the-art policies listed here. In large-scale continual learning problems, uniform balance selection has been shown to outperform more sophisticated policies. A recent CVPR paper examined various existing rehearsal policies in compute-constrained continual learning settings. They found that advanced policies did not demonstrate any clear advantages over simple uniform class balance sampling. In our TMLR paper, we studied several principled rehearsal policies in continual learning on an ImageNet subset and a long-tail dataset. We found that uniform balance selection outperformed more sophisticated policies. This is consistent with prior studies. Uniform random sampling is a strong baseline in continual learning and has also proven to be a highly effective strategy for active learning and dataset pruning, as demonstrated by several works. For the first time, we demonstrate that our method GRASP outperforms the uniform balanced rehearsal policy while enhancing computational efficiency. Specifically, GRASP matches the best performance of the uniform balanced approach while requiring 40% fewer gradient descent updates and 36% less training time for class incremental learning with the siesta rehearsal algorithm on full ImageNet 1000 dataset. Therefore, GRASP stands out as the most effective rehearsal policy to date. Now let's discuss how GRASP works. GRASP is based on the hypothesis that choosing only easy or hard samples are both suboptimal, and that the deep neural network would benefit from a curriculum that combines both. GRASP first selects the most prototypical or easy samples from the replay buffer and then gradually selects harder samples, where easy samples are closest to the class mean and hard samples are farthest. Severe catastrophic forgetting in minority classes can occur in rehearsal due to class imbalance, which GRASP overcomes by selecting samples in a class-balanced way, where minority classes can be oversampled. Now we can ask, why is GRASP more effective? An efficient rehearsal policy should not perturb previously learned representation, otherwise training overhead increases with an increase in representation drift. While learning new classes, the representation of old classes abruptly change and drift over time. This abrupt change in old representations causes catastrophic forgetting of old knowledge and is difficult to correct without longer training. As shown in this figure, existing methods exhibit higher representation drift. These methods mostly prioritize difficult samples. For instance, MIR and SR select samples with maximum interference. Consequently, the old representations are excessively perturbed, especially in the early stage of rehearsal, indicated by the sharp rise in mean squared error. In contrast, GRASP reduces representation drift by learning from subsets of increasing difficulty levels. Therefore, GRASP achieves higher accuracy and efficiency by mitigating representation drift. Now I will describe experimental results. We conducted a comprehensive experiments evaluating numerous rehearsal policies, comparing GRASP against 17 other rehearsal methods, including 3 gradient-based methods. We performed these experiments on ImageNet subsets using the siesta algorithm with latent rehearsal for class incremental learning. We found that GRASP outperformed all 17 compared methods, demonstrating superior performance. Here we show the most performant methods. Notably, GRASP consistently surpassed the uniform balance rehearsal policy, which earlier works found was the most effective policy for large-scale datasets. To validate that GRASP performs effectively under varied memory and compute constraints, we compared GRASP with competitive rehearsal policies under varied memory and compute constraints. We performed these experiments on ImageNet subsets using the siesta rehearsal algorithm with latent rehearsal for class incremental learning. We found that GRASP consistently achieved the highest accuracy across all constraints, highlighting its robustness and efficacy in diverse settings. Now the question arises, how efficient is GRASP compared to current state-of-the-art methods? Here we evaluated different methods in terms of training time relative to the uniform baseline. Unlike GRASP, existing state-of-the-art methods require significantly longer training time, making them computationally prohibitive to scale. Specifically, gradient-based methods are notably expensive. For instance, grad matching requires 97 times more training time than GRASP. This comparison clearly demonstrates that GRASP is significantly more efficient and scalable than existing methods. Here we assess GRASP's ability in large-scale continual learning on ImageNet 1000 under a variety of scenarios such as latent rehearsal and veridical rehearsal. Both GRASP and Uniform Balanced use the same rehearsal algorithm siesta in class incremental learning scenarios. We observed that in both latent and veridical rehearsal settings, GRASP consistently outperforms Uniform Balanced policy. We also conducted a statistical analysis. Using McNemar's test, we compared the predictive accuracy of GRASP and Uniform Balanced policies and found that they were significantly different in all cases. An ideal rehearsal policy should excel regardless of distribution. Class incremental learning is an extreme adversarial setting where catastrophic forgetting is severe. Here we considered the other extreme, independent and identically distributed or IID setting where catastrophic forgetting is minimal. In this slide, we show that GRASP surpasses uniform balanced policy in both class incremental learning and continual IID orderings. This demonstrates that GRASP works well with arbitrary data ordering. We also conducted a statistical analysis. McNemar's test showed a significant difference between GRASP and uniform balanced policies. When combined with the siesta rehearsal algorithm, GRASP outperforms uniform balance policy in both latent and veridical rehearsal settings with and without storage constraints. These comparisons are based on class incremental learning on the full ImageNet 1000 dataset. This demonstrates that GRASP is an effective rehearsal policy in both unbounded storage and bounded storage settings. Statistical tests further confirmed that significant difference existed between GRASP and uniform balanced policies. We also investigated the efficacy of GRASP when paired with other popular rehearsal algorithms such as DAR++ and GDUM. Our observations indicated that when combined with DAR++ and GDUM, GRASP achieved higher accuracy than the uniform balanced policy in class incremental learning on full ImageNet 1000 dataset for both latent and veridical rehearsal settings. These results demonstrate that GRASP is general and has wider applicability. Now I will discuss additional experimental findings. Using the IDB or rehearsal algorithm, we evaluated GRASP and uniform balanced rehearsal policies in continual text classification. They performed task incremental learning with various task sequences based on 5 benchmark datasets. We also imposed compute and storage constraints. We found that GRASP exceeded uniform balanced in 5 out of 6 task sequences. This demonstrates GRASP effectiveness in both vision and NLP tasks, highlighting its greater generality. We also conducted long-tail recognition experiments. Besides balanced data streams, a rehearsal policy should also work for long-tail data streams since real-world data distributions are often imbalanced and long-tailed. In both unbounded and bounded memory settings, GRASP exceeded uniform balanced in class incremental learning on the Places 365 long-tail dataset. Finally, to examine GRASP efficacy in a vision transformer architecture, we conducted continual learning experiments using mobile VIT with siesta algorithm. GRASP outperformed uniform balanced in class incremental learning on the ImageNet 300 dataset. Therefore, GRASP shows efficacy for both convolutional neural network and vision transformer architectures. In summary, GRASP is a scalable, faster, and computationally efficient rehearsal policy. It is much more efficient than existing state-of-the-art rehearsal policies in the large-scale dataset regime. GRASP is the first rehearsal policy to outperform the uniform balanced policy, which is a strong baseline in large-scale continual learning settings. Furthermore, GRASP is robust to various data orderings, achieving top performance in class incremental learning, IID, and long-tail distributions. GRASP works well with various rehearsal algorithms and is a highly effective rehearsal policy compared to others on both large-scale image and NLP datasets. Periodic retraining is currently the industry standard for updating deep neural networks. We believe GRASP has potential to supplant this extremely computationally expensive process with much more efficient continual learning methods. And therefore, GRASP can contribute to the reduction of carbon footprint from training models. Likewise, GRASP can be used to make on-device continual learning more efficient where both compute and memory are heavily constrained. Finally, I want to thank the US National Science Foundation for funding our research. Thank you for your attention.